Okay, so now we're recording. All right, so we'll just record until the battery runs out. So in this case, you have a 70 kilogram dude and a 30 kilogram dude, and you don't have distances. What you have instead is x, and not x. So if the bar is 10 meters long, and the distance from the 70 meter dude to the fulcrum is x, what's the distance for the 30 meter guy or 30 kilogram?
X.
Yeah, 10 minus x. Okay, so this distance would have to be 10 minus x. So this kind of thing is pretty common. Now the torque, we're going to ignore the mass of the bar. The torque is still whatever the force you have on the left is times the distance on the left equals whatever force you have on the right times the distance on the right. Again, torque left torque left equals torque right. Okay. So you still have, we're going to assume they're on the planet, so you still have 700 newtons multiplied by, in this case, x equals 300 newtons multiplied by this case, 10 minus x. Okay? You can still solve this. You can still solve for x. Figure out where the fulcrum is. So go ahead and do that. Rub a little algebra on this and figure out what is x that makes it balanced. Sounds about right? About 3 meters? Okay. So, they gave us nice whole numbers, but should you find a situation where you're not given the distance, you're only given a proportion, just, yeah, that's how you do it. Just math it. Rub a little math on it. Okay. Button. Here's my button.
I knew I got one.
So how's this torque stuff going? Most of you did pretty well in the labs. So, okay. As long as you ignore the mass of the bar, we're happy. And I think right now that's all I want to do. I just want to always ignore the mass of the bar. It's going to be a little tricky when you make your torque mobiles because the mass of your bar might not be insignificant. It might be significant. But I don't really want to go into this unless we take physics AP, then we'll need to know the mass of the bar, but I don't really want to go into this right now. I do want to move on. Okay. So, circular motion. Here's my spill knot. I have a spill knot. This is called the incredible spill knot. And it actually is found at spillknot.com. And I'm going to put some water in my spill knot in a plastic container. You guys better pay attention. It might splash you. So these things have been around for hundreds of years. They used to be used in like tea sets. They bring the tea this way. And you're like, woo, and you're like running around the corner, like, watch out, Lena, watch out, Angelina, oh, it's coming at you. Yeah, it's pretty cool, and you can do all sorts of cool stuff with it, including go all the way around. Yeah, you're like, whoa, he's gonna splash stuff. As long as you realize that there's a flag right there and there's a light right there, you can go all the way around and don't have to worry about spilling it, because it's called the spill knot. You're like, is it glued? No, it's not glued.
Oh.
Okay. Yeah, but what was going on there?
When you're resisting,
Yeah, so you've been told that this is force called centrifugal force with an F. I'm telling you right now that centrifugal force doesn't exist. And what does exist is something far more common. Well, centripetal force exists, and we're going to learn about that. But what kept the water in? what kept the water in on the spill knot in the cup? Why did it stay this way? Friction helped. Yeah, definitely friction helped. If there was no friction, that'd be an interesting situation. Yeah. But more importantly, inertia. Inertia is very important.
Yes.
In fact, if you were to look at this, as I spun it around in a circle, you would have noticed, if you slowed it down, that the water was no longer parallel to the surface. The water actually did something kind of interesting. It moved a little bit, which is why if I fill this all the way to the brim, I can't do it anymore. Because the moment I do this, the water will slosh out. It's not parallel to the surface anymore. It's at a bit of an angle because of the inertia. So let me show you what I mean. When you have something going around in a circle, around and around in a circle. If something here is moving this direction with a velocity this way, there has to be an acceleration towards the circle to cause it to turn. Which means, what produces an acceleration? Forces, yeah. Which means there had to also be a force. And there also had to be some sort of force in that direction pulling inward. This force is called centripetal force. And that causes the water to change direction. It causes anything to change direction. Similarly, when you're driving in your car and you want to turn left, you turn your wheel this way, your car goes left, and your coffee goes right from inertia. And that's what's happening here. If you were to actually draw this, the spill knot. There's the spill knot, aimed that way. If you were to draw the spill knot, what you'd see is the water is not like this. The water is in fact there. It's actually trying to keep going backward. Sorry, not that way. This way. It's trying to keep going where it wanted to go. It's like, no, I'm going that way. I'm going this way, so the water sloshes in that direction. It sloshes that way. And we're going to learn more about fluids in a spring, but anyway, that's what it looks like. Okay, so let's talk more about circular motion. There is, of course, some formulas involved. Okay, so the time it takes for one around is called a period. And we're going to use this idea, and we're going to use this idea of a period quite a bit this spring. So the time for one all the way around is called a period. We're going to use this when we do harmonic motion, waves, and the whole shooting match. But the time to go all the way around is one period. Now, the circumference of a circle, so if this is r, that's the radius r, the circumference is given by the formula, what? 2 pi r. Yeah, good. I'm not a big fan of 2 pi r. You can also think of it as 2r pi. I learned it as diameter times pi. But this is actually important too, because this links the idea of a radian or a circle to the circumference. Yeah. Okay. So yeah, 2 pi r. That's our circumference. So the velocity to go all the way around the circle would be how far you go around the circle, v, which is d over t, right? So if you're going in a straight line, it's d over t. If you're going around a circle, it's 2 pi r over big T. That's the time to go all the way around the circle. The inverse of a period is a frequency. If period is how many seconds it takes to go around once, frequency is how many around onces you get in a second. So period is how long it takes to do one thing. Frequency is how many things you get in 1 second. So again, period is the time it takes to go all the way around. And frequency is how many all the way arounds you get in 1 second. And of course, they're mathematical inverses. Circumference is 2 pi r. Direction of velocity is tangent to the circle. So if you want to know how fast you're going in a circle, it's 2 pi r over big T. So the circumference is 2 pi r, all the way around the circle. And the velocity is distance divided by time. Well, if the time to go around the circle is big T, period, then the circular velocity, Gesundheit, is 2 pi r over T. Now, why is this important? Well, if you're playing dodgeball, if you're playing tetherball, and you're really good at tetherball, you hit the ball, it goes around the pole, and someone's like, "I hate you. I'm going to ruin your tetherball game." They whip out a knife, you got a razor blade, and you hit the ball really hard, and they cut the rope, then it's going to travel in a straight line with the same circular velocity. It will have a tangential velocity that is equal to the circular velocity. So if it's going around and around and around and around at 88 meters per second, and you cut it, it's going to go 88 meters per second in a straight line. Okay. It's going to have the same tangential velocity as it has circular velocity. Like a utility. Home Depot. Oh. Maybe lights. Okay. Now the acceleration is inward towards the circle. We learned this when we did vectors, that acceleration has to exist for a velocity to change. Well, if you want the velocity to change direction, just put your acceleration perpendicular to your velocity. Okay, so far so good? All right, cool. So there's this thing called the hammer throw, and basically it's on the end of a chain. There's a ball, steel ball, and there's a handle on the other chain. And what happens is the athlete goes around and around and around. You can kind of see in the animation. Woo! Bonk. Unless let's hit that chick right there. So that's a hammer throw. So you have to go around and around really fast, right? Because the faster you go circularly, the faster the hammer will go tangentially, right? So if you're going around at 2 meters per second and you let go, the hammer's going to go at 2 meters per second. If you go at 60 meters per second, you let go, the hammer goes at 60 meters per second. Well, why do you have to be so strong? You have to be so strong because you have to produce that acceleration. Okay. There's some relationship between the acceleration that you have to produce and the velocity. In other words, the faster that velocity is, the bigger that acceleration has to be. And the bigger that acceleration has to be, the bigger that force has to be. Does that idea make sense? So if I want to go really fast, have a big V, that means I'm going to need a big A. And to get a big A, I need a big F. There's a relationship, of course. First and foremost, Newton's first law, F equals ma. Only we're going to add some subscripts. Fc equals mac. In other words, the force you have to pull inward, this is called centripetal force, which literally means center-seeking force. Like the petals of a flower are attached to the center. Centripetal force literally means center-seeking force. So the bigger your Fc is, the bigger your AC can be. Does that idea make sense? And there's a relationship between AC and V, and it's pretty cool. AC equals V squared over R. Is that up there somewhere? Yep, there it is. AC equals V squared over R. Hey, look, it's right there. So the bigger the more force you apply, the more acceleration you can apply. And the more acceleration you can apply, the bigger your velocity will be. Which is why hammer throwers are basically triangular. They have massive, massive upper body strength, so they can pull inward. And the more they can pull inward, the more centripetal force they can apply, the more centripetal acceleration they can apply, and the more centripetal acceleration they can apply, the more circular velocity they will have, and the more circular velocity they will have, the more tangential velocity they will have. And the more tangential velocity you will have, the further your projectile will travel. Get the idea?
So they got the Dorito bomb?
Yeah, and then someone's on the other end of the field with a basket.
Oh, I would not want to be that guy.
Yeah.
Do they have like really weak legs or something?
No, they still need really strong legs.
Like,
But
why do
yeah, they need massive, massive upper body. They still have strong legs because you still have to spin. You have to basically support yourself. But yeah, there has to be massive, massive upper body strength. Yeah.
So it's like when you're in a chair and you're like spinning and then you like tuck in more and spin faster.
Yes. Yes. And we're gonna talk about that idea pretty soon too. Okay. So if you like things on screens, what direction is the thrower exerting force? Inward. Yeah. He's applying an inward centripetal force to produce an inward centripetal acceleration. And as he applies that inward centripetal acceleration, he's going to produce an as he's applying inward centripetal force, he's going to apply an inward centripetal acceleration, and then that inward centripetal acceleration is going to produce a velocity equal to AC equals E squared over R. So if you like things on screens, there you go. Skylab was our first habitable satellite that we launched into the sky. You probably never heard of it. It was back in the 60s and 70s. And then the Russians launched Mir, and Mir was up there for a long time. Mir only came down in like the early zeros. Taco Bell had a little target, like if the Mir hits the target, everybody gets a taco. And then we built the International Space Station. These space stations, they didn't have any relative gravity. In other words, they were falling towards the Earth as fast as everything else in the sky was falling towards the Earth. But when we build habitable space stations for the long term, or spaceships that need to go several months to Mars, they're going to have to spin. Why?
They have gravity.
Exactly. They're going to simulate gravity. They're going to have simulated gravity. They're going to spin so they have simulated gravity. In other words, when they spin, there's going to be a normal force that you're going to feel in your feet on the outside of the space station. Yeah. Okay. Let's make a space station. So there's our space station. Okay. I can't. If I look at the circle, things just go all cattywampus. So here's our space station's right here. There's our space station. And you're going to be right here. The windows for the space station will be on the floor. It's going to spin around and around. It's going to spin this way. Now, how big is our space station? What's the diameter? What's the radius of our space station? 100 yards. 100 meters. Okay. So our space station is 100 meters. What I'd like you to know, what I'd like you to calculate or figure out is how fast does it have to spin to simulate Earth gravity? We have a radius of 100 meters. The radius is 100 meters. How fast does it have to spin to simulate Earth gravity? And this is a one formula field.
Hold it.
Yeah. So our formula is just our favorite formula. We're going to use a lot. AC equals B squared over R. And we're aiming for 10 meters per second squared. ideally, if we're gonna simulate Earth's gravity, most likely we're gonna simulate something a little bit less, just because the faster it goes, the harder it is to stop. So we'll probably shoot for like 8 or 9. That's comfortable. Anyway, and then we're searching for velocity, and our radius is 100 meters. Simple, right? So what's v? 31.3 meters per second.
That's if you use 9.8 as a
33. What is it if you use 10? What's the square root of 33.3 meters per second repeating? So basically the square root of 10,000.
Yeah.
Right. So yeah, that's how fast the outside of the space station will have to spin to simulate Earth gravity. Here's the cool thing. Anyone ever seen Babylon 5? There's a sci-fi show that was on before you were born. My favorite, by the way. And in this show, in this show, basically they have a tram that's around the middle of the space station. So you can get out of the tram and you can just be like, I'm floating, because there's no gravity. There's very little gravity in the middle. How about anyone play the video game Elite Dangerous? No? Okay. Same thing. You fly in, and as you fly into the middle of the space station, there's no gravity. Gravity kicks in as you start getting towards the outside of the space station, or towards the inside. So like right in the middle, there's nothing. As you go this way, your gravity starts building up. It's pretty slick. Yeah.
The velocity is actually 31.6.
Thank you. 31.6. 31.6 is the square root of 10,000.
It's 1,000.
Square root of 1,000.
I feel like I gave
So
him the
if
number.
like there was a space station, and if you wanted to get closer to the center, would it have to spin faster or slower in order to?
If you wanted to move closer to the center, you would have to go slower. The slower you go, the more you drift towards the center. Or as you drift towards the center, you'd be going slower and slower and slower. If you maintained your speed, you kind of you stay there. You stay where you were. Yeah. Okay. Angular momentum. You guys have all seen this, right? I need a little help and then a volunteer.
Is he on my thing? Oh my gosh. Wait, did she?
Well, yeah, it's a GIF. I mean, it's got to actually happen, right?
Guys, let me
Okay, come on up, right? Let's see if I'm. The goal is to center yourself on the platform. Now, what's going to happen is Braden's going to give me a little push, and then I'll take care of it. So give me a little push on back, down on my arm. The platform is very small, and I am very big. Okay. You have better balance than me. You can spin and spin and spin and spin. So basically, I have weights, and my weights are distributed outward. And as I start spinning, I have a little bit of angular momentum. And the math is pretty exotic, but we're not going to deal with much math in this class. We'll deal with it next year. But so if you can be spinning, hopefully I can keep my balance this time. So, as you bring your mass inward, your velocity speeds up, and I'm going to put these here so you guys can practice.
I want to be a figure skater.
Yeah. So if you're a figure skater or you're Tony Hawk and you want to spin, you want to make your mass really small. Or if you're playing football and you want to spin, you want to make yourself as small as possible so you can spin faster. Also helps to protect the ball. But the smaller you make yourself, the faster you'll spin. Well, it turns out all spinning objects have what's called angular inertia. And it's equal to mass multiplied by where the mass is. Okay? It's multiplied by mass times multiplied by where the mass is. The further the mass is away, the bigger your angular inertia. This is partially why it was really hard for Gronk to turn around. Gronk! He's like, no! I'm too big, I can't turn around quickly. Gronkowski. He's the tight end for the New England Patriots. Yeah, who missed the Dolphins guy at the end. It wasn't his fault, he's just too big. It's hard to turn around when you're big because you have all that mass, and that mass is far away. Now if it was a kicker, maybe the kicker might have caught us. So angular inertia is a product of the mass multiplied by where the mass is. Angular velocity is spinning speed. Now again, this is omega given in radians per second. In this class, there will be no calculations with radians until AP. This is what made people cry last year. Like, no radians, wow! So you just need to know the relationships. You don't need to do any math. Okay. So angular velocity is spinning speed, and angular momentum is L. Now there is an analog to linear momentum. Linear momentum is mass times velocity. Angular momentum is angular inertia times velocity. Angular inertia is the analog of mass. So if you're talking about linear things, momentum, P, is equal to mass times velocity. And momentum needs to be conserved.